Now this is the worst that can happen to you when you are rushing out to work. Your fuel meter is sliding dangerously to empty. When it comes to fuels, I prefer CNG, compressed natural gas, my little contribution to cleaner environment. Looking at a CNG cylinder, a question comes to me. Have you noticed that CNG is stored in special cylinders, just like the LPG that you use in your kitchen? Well, that's what we are going to talk about today. While I rush to the studio, you start thinking about that. Hello and welcome to the show on study of ideal gas equation. It was in 1783 that the first air balloon floated in the air. Today, rocket fuels use liquid gas to propel into space. Today I will reveal the science behind all that and more. We will understand the ideal behavior of gases and gas laws, study the ideal gas equation, and finally we have exam decoded, where you will get handy tips for your exams. One of the three states of matter, comprising freely moving atoms and molecules, gases lack a definite shape and volume. Its atoms and molecules move independently and more freely than those in a solid or liquid, with no significant forces keeping them together or pushing them apart. Gases are the only state of matter that can be compressed very tightly or expanded to fill a very large space. So for the ease of handling and storage, gas is often liquefied. And for a gas to be liquefied, a certain amount of pressure and degree of temperature is applied to it. That explains why the CNG in our cars and our cooking fuel are stored in gas cylinders. But there is more to liquefied gases than just these two applications. For example, liquid nitrogen is used as a freezing agent in the food processing industry, and helium, with its extremely low temperatures, is used in particle accelerators for superconductors and electromagnets in nuclear fusion research work. Other gases like methane, propane and butane, or the fuel gases, burn with oxygen in air to provide energy. Let me introduce a term that is central to our session today: ideal gases. Before that, some background information. Now, we know that gas laws deal with how gases behave with respect to pressure, volume, temperature and amount. Despite differences in chemical properties, all the gases more or less obey gas laws. Now, an ideal gas is defined as one in which all collisions between atoms or molecules are perfectly elastic. The molecules undergo perfectly elastic collisions with the walls of the container while in constant random motion, in which there is zero intermolecular attractive forces. One can visualize it as a collection of perfectly hard spheres which collide but otherwise do not interact with each other. When does a gas qualify to be an ideal gas? Well, there are 6 postulates that it should follow. Let's look at them. First, gases are composed of minute discrete particles. That is, the constituting particles of gas occupy no volume. Second, particles are in continuous motion. That is, they move in straight lines between very frequent collisions with each other and the sides of the container with approximately 10 raised to the power 9 times per second. Third, the bombardment of the container walls by the particles result in the phenomenon we call pressure. That is, the force of impacts per unit area. Postulate number 4, the collisions should be perfectly elastic so that no energy is lost on collision due to friction. The fifth one states that at a relatively low pressure, the average distance between particles is large compared to the diameter of the particles, so that the intermolecular forces between the particles are negligible. Thus, there are zero intermolecular forces between particles. Finally, the sixth postulate states that the average kinetic energy of the particles is directly proportional to the absolute temperature in the Kelvin scale. Now, let me ask you a quick question here. When was liquefied petroleum gas first produced and by whom? Think about the answer while I go for a break. I'll be back shortly with the answer and much more. Stay tuned. Welcome back to the show on ideal gas equation. Here is the question I had left you with before the break. When was liquefied petroleum gas first produced and by whom? And the answer is, it was first produced in 1910 by Dr. Walter Snelling, and the first commercial products appeared in 1912. Now, you have seen that gases can be stored in special pressurized containers. But the gas never settles down at the bottom of the cylinder in one heap like solid or liquids, and is in fact dispersed around the container. So why does the force of gravity not pull down all the gas molecules to the bottom of the cylinder? When you look at a gas microscopically, you can see that the thermal motions of the molecules help them to scatter around the chamber. For example, many microscopic collisions of the molecules with the piston appear macroscopically as a smooth pressure exerted by the gas on it. As the pressure increases, the volume decreases if the temperature is kept constant. You have learned this in Boyle's law. You have seen how the motion of molecules of a gas are affected by heat, pressure and volume. Now we will relate all these and derive the equation of ideal gas. It is a combination of two gas laws, Boyle's law and the Charles law. Boyle's law is named after a chemist and physicist, Robert Boyle. This law describes the relation between the product of pressure and volume within a closed system as constant when temperature remains at a fixed measure. Pressure and volume, both entities remain inversely proportional according to the law. Boyle's law states that for a fixed amount of gas kept at a fixed temperature, pressure P and volume V are inversely proportional. The mathematical equation for Boyle's law is P into V is equal to K, where if 1 mole of gas at constant temperature T1 is subjected to a change in pressure from P1 to P2 and the volume changes from V1 to V, then as per Boyle's law, P1 into V1 is equal to P2 multiplied by V, or V is equal to P1 V1 divided by P2. For further reference or calculation, we will mark the equation as 1. The temperature T1 in this equation is constant. Now, just as Robert Boyle made efforts to keep all properties of the gas constant except for the pressure and volume, the famous French scientist Jacques Charles took care to keep all properties of the gas constant except for temperature and volume. Charles' law states that at constant pressure, the volume of a given mass of an ideal gas increases or decreases as its temperature in Kelvin increases or decreases. Let me show you how this law can be mathematically represented. According to Charles' law, V upon T is equal to constant K. We will now apply this law to 1 mole of a gas at constant pressure P1, whose volume changes from V to V2 and temperature changes from T1 to T2. As a result, V by T1 is equal to V2 upon T2, or V equals V2 into T1 by T2. We will mark this equation as 2 for future references. The pressure P1 in this equation is constant. Now, from Boyle's law, we have V is equal to P1 V1 by P2. Equating the two equations, we get P1 V1 by P2 is equal to V2 T1 upon T2. On rearranging, we will get the equation as P1 V1 by T1 is equal to P2 V2 by T2. On the other hand, P into V by T is equal to a constant represented by R. So, the equation for 1 mole of a gas is PV is equal to RT. If there are n number of moles, the equation becomes PV is equal to nRT. R is called the universal gas constant, and this equation is called ideal gas equation. And all gases which behave as per the ideal gas equation are called ideal gases. The ideal gas equation has a wide range of applications. This equation is one of the fundamental principles used in calculations involving gas flow in air pollution. It is also used to calculate actual gas flow rates based on the quantity of gas present at standard pressures and temperatures. The equation is used to determine the total quantity of a contaminant in a gas that can participate in a chemical reaction. So, we can conclude that the volume occupied by a gas is a function of 3 parameters: number of moles in a gas, absolute temperature, and absolute pressure. Since the volume of a gas is affected by the change of its temperature or pressure, we can derive the gas volume of 1 mole of gas at STP very easily from the ideal gas equation. STP is standard temperature and pressure, where pressure is 760 millimeters of mercury and the temperature is 0 degrees Celsius. To find the volume first, convert temperature from degree Celsius to degree Kelvin, wherein 0 plus 273 gives the temperature at 273 Kelvin. Then convert pressure from units of millimeter mercury to atmosphere. Since absolute pressure equals 760 millimeter of mercury, it amounts to 1 atmosphere. By substituting the values of pressure, temperature and gas constant, you will get the gas volume as 22.4 liters. Similarly, pressure too can be calculated in a given set of conditions. At this point, we have a student with a very pertinent question. Let's hear it out.
Even though ideal gas equation is applicable to all gases, does it have any limitations?
I was just going to address it. Does the ideal gas equation have limitations? It does. As you are aware, the ideal gas equation is based on the assumption that the molecules of a gas are independent of each other and are so far apart that the volume of the gas is that of the container it occupies. However, at high pressure and low temperatures, gas molecules come very close to each other and we have to consider the actual volume of the gas. We will also need to take into account the effect of intermolecular forces between the gas molecules, as in close proximity they will hold on to each other with greater force. With these limitations, I am sure you understand ideal gas laws much better. I am going for a break now, after which is the section that makes you breathe easy in exams, the exam decoded segment. So stay tuned.
Thank you.
Welcome back to the show. Before we proceed, let's do a quick recap of what we have covered in today's episode. An ideal gas is defined as one in which all collisions between atoms or molecules are perfectly elastic and in which there are no intermolecular attractive forces. The ideal gas equation relates pressure, volume, temperature and amount of the gas and is represented as PV is equal to nRT. 1 mole of a gas occupies 22.4 liters at STP. Limitations to ideal gas equations arise at very low temperatures and high pressures as the assumptions about the actual volume of the molecules cannot be ignored in comparison to the volume occupied by the gas. Also, the molecules will hold each other with a considerable intermolecular force. With that revision of today's session, I am sure you are now prepared for the exam decoded segment. This is the exam decoded segment where we look at tips and tricks to better your scores in the exams. We begin with our rapid fire round. 5 quick questions of 1 mark each that will help you rate your preparedness for the exams. You will get 5 seconds to answer each question, and in the end, the score analysis will help you rate your performance according to your scores. Ready? Here we go. Question 1. Gas can be liquefied under what conditions? A. Low pressure. B. Low temperature. C. High pressure and low temperature. D. None of the above. The correct answer is C. High pressure and low temperature. That was very easy and I hope you got it. Moving on. Which law relates pressure and volume at constant temperature for an ideal gas? A. Charles' law. B. Boyle's law. C. Avogadro's law. D. Gay-Lussac's law. The answer is B. Boyle's law. Next. At STP, 1 mole of gas will occupy A. 22.4 liters, B. 24.4 liters, C. 24.2 liters, D. 42.4 liters. The answer is A. 22.4 liters. The fourth question is, pressure exerted by the gas molecules is due to the collision between the gas molecules in the container. True or false? The answer is false. Pressure exerted by the gas molecules is due to the collision of gas molecules on walls of the container. On to the last question. Ideal gas equation is also called equation of state. True or false? The answer is true. Ideal gas equation is also called equation of state. And that brings us to the end of the quiz round. If you have given all the correct answers, then you surely are a high flyer, well on your way to becoming a topper on ideal gas equations. Good job. If you have nearly gotten there, you are still quite an achiever with 3 to 4 correct answers. And if you have got less than 3 right answers, you are a learner with some distance to cover. And for that, keep watching the shows and log on to our website www.topperlearning.com for all the practice that you need. Your scores in the exams are a function of how smart you prepare and not just how hard. And for that, you need to know how many marks each unit carries in your exams. The topic, ideal gas equations, belongs to the unit states of matter and can get you 4 marks. Questions asked from this topic can be very short answer type questions for 1 mark and short answer type questions for 2 marks. Typically, questions asked from this topic test your numerical ability. Now, since it is numerical problems that you need to work on, we have a few examples for you right here based on previous year's trends. How many moles of gas are in the sample of a gas which occupies a volume of 20 liters at 25 degrees Celsius and a pressure of 5 atmospheres? Gas constant R is equal to 0.0821 liters atmosphere per Kelvin per mole. This is worth 2 marks. To solve this answer, you must use the ideal gas equation PV is equal to nRT. Identifying this base equation will get you 1 mark. Now, if you list the data given, you will see volume V is equal to 20 liters, temperature T is equal to 25 degrees Celsius or 298 Kelvin. Pressure is equal to 5 atmospheres. Gas constant R is equal to 0.0821 liter atmosphere per Kelvin per mole. After substitution of the values in the ideal gas equation, we can calculate N, that is the number of moles, to be 4.08 moles. This value along with the correct unit will get you the final mark. Now to guide you through ideal gas equations, we have an exam expert with some more advice on how to prepare this topic for your exams.
Students, in this chapter ideal gas equations, you have to remember that this is an equation which gives you the combined effect of pressure and temperature on the volume of a gas. While solving this equation PV is equal to nRT, the basic error you commit is while putting the values of R. The value of R is determined by the units of pressure and volume. If the units are liter atmosphere, then the value of R is 0.0821. However, if the units are Pascal meter cube, then the value is 8.314 joule per Kelvin per mole. Remember, when you are using this equation for two different states, P1 V1 upon T1 is equal to P2 V2 upon T2 is the equation, where the basic error is in the units of temperature. The units have to be put always in Kelvin.
I am sure all these tips have boosted your confidence to face your exams. Remember, stick to the basics, write each step, think calmly, and nothing will stop you from scoring 100% marks. After all, the harder you work, the luckier you get. See you next time.